Have you ever wondered how your GPS just knows the fastest route? Like, instantly? Dodging traffic, avoiding that new construction downtown? Well, it's not magic, it's actually math. And today, we're going to pull back the curtain on the incredible logic that makes it all happen. Dijkstra's algorithm. Let's get into it.
It all boils down to a question you've probably asked a million times. You're here at Town A, and you need to get all the way over to Town B. You can see a bunch of different roads, so what's actually the quickest way to get there?
Okay, so to figure this out, let's just imagine a simple map. We've got a handful of towns, all connected by these different roads. And of course, each road takes a different amount of time to travel. Some are quick little hops, others are long, winding routes. Our job is to find the best possible path.
And that's really the key here, right? We're not just trying to find any old way to get to Town B. We are on a mission to find the optimal route, the one path that adds up to the absolute minimum amount of time. This is what's known as a shortest path problem.
Now, for a computer to get this, we've got to learn to speak its language. We need to translate our little map into some computer science terms. And what we're really looking at here is a classic example of something called a graph.
All right, first up, the towns. In graph theory, we don't call them towns. Each location or point on the map is called a vertex. Pretty straightforward, huh? Town A is a vertex, Town B is a vertex, you get the idea.
And what about the roads connecting all those towns? Well, those are called edges. An edge is just the line, the connection, between any two vertices. So that road from Town A over to Town C, that's an edge.
And here's where it all comes together. As soon as we put those travel times, those numbers on the roads, our simple graph becomes a weighted graph. Each edge now has a weight, which is just the cost of traveling along it. Now that we've got the lingo down, we can finally put this algorithm to work.
All right, so how does Dijkstra's algorithm actually find that shortest path? It's a really beautiful, step-by-step process. It just explores the map and updates its notes as it goes. Let's walk through it together.
So first things first, we need a way to keep track of the best time we've found so far to get to every single town. But at the very beginning, we haven't gone anywhere yet, so we have no idea how long it takes. We'll label every town with a cost of infinity. The only one that's different is our starting point, Town A. It costs 0 minutes to get there, because we're already there.
Believe it or not, the whole algorithm just comes down to 2 simple steps that we're going to repeat over and over again. First, we look at where we can go from our current spot and update our time estimates. And second, we pick the cheapest, unexplored town to go to next. That's literally it. Let's see how it plays out.
All right, let's kick this off. We're at Town A, where the cost is 0. Looking at the roads from here, we can see a path to Town C that takes 3 minutes. So we'll update C's label from infinity to 3. We also see a road to Town F that takes 2 minutes, so we'll update its label to 2.
And now for step 2. We just look at all the towns we haven't fully explored yet and pick the one with the lowest cost. So we've got Town C at 3 minutes and Town F at 2 minutes. The choice is obvious, right? We're going to Town F next, and from now on we'll consider Town F explored.
And here we go again. Just rinse and repeat from our new spot, Town F. Now remember, it cost us 2 minutes to get here. So from F, the road to Town B takes another 6 minutes. The total cost from the start is 2 plus 6, which is 8. The road to G is 5 minutes, so that's a total of 7. And to get to Town E, it's 3 minutes, making the total 5. Let's update all their labels with these new, better times.
Now, pay attention here because this is a really important rule. Look at the path from F to C. That road takes 2 minutes. Since it already cost us 2 minutes to get to F, the total path would be 4 minutes. But wait, our current best time for Town C is already 3 minutes. Since this new path is actually slower, we just ignore it. We only update if we find a faster route.
Okay, back to step 2. Let's look at our list of unexplored towns. We've got B at a cost of 8, G at 7, E at 5, and C is sitting there at 3. The lowest one is Town C, so that's exactly where we're headed next. Time to explore from there. Okay, let's see what we can do from Town C. It cost us 3 minutes to get here, remember? Well, from C, there's a little road to Town E that only takes 1 minute. The total journey time is 3 plus 1, which is 4 minutes. Hey, that's way better than the 5 we had for Town E before. So we'll go ahead and update E's cost down to 4. See how the algorithm is constantly getting smarter as it goes?
Time to pick our next move. Looking at the unexplored towns, B is at 8, G is at 7, and now E is at 4. The cheapest is definitely Town E.
And this is where the genius of the algorithm really shines. Because we always choose the cheapest path to explore next, we can lock in that value. We now know for a fact that the absolute fastest way to get to Town E is 4 minutes. Why? Because any other possible route would have to go through a town that already costs more than 4 minutes, so it can never beat the path we just found.
We are so close. Let's see what we can do from Town E, which we've now locked in at a cost of 4 minutes. There's a road straight to our destination, Town B, that takes 2 minutes. That gives us a new total travel time of 4 plus 2, which is 6 minutes. Our old estimate for B was 8, so this is a huge improvement. Let's make that final critical update.
And there it is. We look at our list of remaining unexplored towns, and Town B is now the cheapest at 6 minutes. And since B is our destination, we can stop. We've done it. We've found our answer. The fastest possible route from Town A to Town B is exactly 6 minutes.
So that's the big idea. But there's always a bit of fine print, right? To make this work in the real world, like on your phone's map app, there are a few important details that make it super efficient and powerful.
First off, you might be asking, how do we know the actual directions, not just the final time? Easy. Every single time we update a town's cost, we also jot down which town we came from. Then, at the end, we just trace our steps backward to get the whole path. Second, there's one golden rule: no negative numbers. You can't have a road that takes -2 minutes to travel, right? So for maps, this is never a problem. And third, how does the computer instantly find the cheapest town to visit next? It uses a clever data structure called a priority queue. Think of it like a super organized to-do list that always keeps the best option right on top.
So you might be thinking, okay, that's a neat little map puzzle, but this thing is so much more than that. This algorithm, which is almost 70 years old, is an absolute pillar of modern technology.
I'm telling you, this thing is running behind the scenes all over the place. When you send an email, it helps find the most efficient route for the data to travel across the internet. Delivery companies use it to plan their routes. It's even used in biology to analyze DNA. Finding the shortest path is just a fundamental way of solving problems.
And that kind of brings us to a final thought for you to chew on. Now that you get the logic, finding the most efficient route between a start and a finish, where else could that apply? Maybe it's the steps to finish a big project, or the path to reaching a career goal. What's the shortest path in your world?